G'day. This particular video is going to be quite a short one. We're going to look at one function to explore what happens when you have multiple asymptotes and a change of value in the numerator of these particular kinds of functions. Now, I'm assuming you've been watching this as part of a series. If you're not, let me give you a little bit of context. We have been discussing functions, particularly rational functions of this form, where we have a polynomial divided by another polynomial. And I've branched out and explored a whole variety of principles associated with graphing these sorts of initially functions, but also relations. Sometimes they can get quite complex, because I've ended up with things like this. On this side, if we have a range of things like this, now I'm making these up. I've got two negative ones. Let's make it positive. Let's make another one, y plus 6. Over here, let's make it 3 vertical asymptotes: x minus 4, x plus 1, and x plus 5. And what I'm wanting is to explore what happens when this is not a constant. Now, when it's a constant, we have 3 vertical asymptotes, and this time we'll have 4 horizontal asymptotes, and the graph will fit into the boxes they create, a bit like on a chessboard. All that's well and good. In other videos we've discussed double asymptotes and triple asymptotes and things. Won't go exploring that this time. I want to have a look at what happens here. Now I'm going to put in a factor between minus 4 and plus 1. Let's put minus 2. And I'm going to put one between the 1 and the 5. So let's put x plus 3, smack in the middle. And let's see what this does to the graph. Now, it's such a big equation, I've restricted room for my graph, but we'll do the best we can. Now, I've kept my numbers down below 6, so let's go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Counting is such a big part of mathematics. Let's draw our asymptotes. Well, we have lots of them. We have 3 vertical asymptotes here. They're quite easy to pick because it's already in factored form. Our first asymptote is where x is 4. Here it is. Now, oh goodness, just trying to line it up. That's an asymptote because, simply put, x cannot equal 4 in this equation, because if it was, you'd have 4 minus 4 is 0, and you can't divide by 0. It really doesn't matter what's on the top, even if it is 0. This is just nonsensical. So the graph really can't touch that line. When x is worth minus 1, we have the same problem. So here we are at minus 1. And when x is minus 5, we have the same problem. So we have 3 vertical asymptotes. Now, you can appreciate if we move these up and move these down, we have the same situation with these 4 factors here with y in them. Y can't be worth 1, so we have a horizontal asymptote at y equals 1. Y can't equal 4. So you can see we can get some quite complex graphs with very simple structure. Y can't be minus 3. There's minus 3 there. And y can't be worth minus 6. Now that's this has successfully divided this entire region into 1, 2, 3, 4, 5 into 20 sections. That's quite huge. Now, if this numerator was a positive number like 1 or 3 or 17 or something like that, it means we would start in the top right hand section and our graph would be here and then just like a checkerboard pattern, in here and here and here and here, just all the diagonal patches. So it would be in 10 sections, half of them. If it was a negative number, we wouldn't start here, we would start here. So instead of being here and here and here, it would be here and here, diagonals, and then following the same pattern. So it would be the other 10 regions. Now the problem is, because we have a function of x, sometimes this expression is going to be positive and sometimes it's going to be negative. Well, I think you can see for very big values of x, taking away 2 and adding 3 to them is not going to make any real difference. And multiplying is going to give us a big positive value. So certainly for x up here, it's behaving as a positive, in fact it will be a positive number on the top. But we have a problem when x is worth 2 and a problem when x is worth minus 3. So I'll get my purple pen because I've been using that for graphing. When x is worth 2, here it is here, it would make this 0. So we would actually have a 0 on the top, which would mean this would have to be 0. Now if this was 0, then either that is 0, this is 0, this is 0, or this is 0. And there are our 4 asymptotes. So it means that in effect, when x is worth 2, the function is actually going to have to sit, oddly enough, on the asymptote. Now, an asymptote means the curve will get closer and closer and closer as you go out towards infinity. But it doesn't exclude the possibility that the graph will cross it somewhere in the middle. So there we go. We actually have 4 locations lined up on x equals 2 on the 4 different horizontal asymptotes, where the curve's suddenly going to decide to do something different, because above here this is going to be positive and below here it's going to suddenly become negative. Because you can appreciate when you put x equals 1, 1 minus 2 suddenly makes this negative. Now the problem is that's not the only point. We've got another point at minus 3. Where are we? 0, 1, 2, minus 3. And similarly, when x is minus 3, we get a 0 here, and I don't care what this is worth, anything times 0, this will be 0. And I should say there's no x plus 3 on the bottom either, so this will not be 0 when you put x equals minus 3 in. So all that's worth 0, which means these will have, one of these, or they can take turns being 0. So y equals 1 would sit well with this being 0, and y equals 4. So again we have these 4 points on the 4 asymptotes lined up on x equals minus 3. So what's going to happen? On this side, the graph's going to start exactly as we expected, with a positive section here, and then it would switch over to do this little bit in here, then it would have a section in here, and it would switch over to do a little section in here, and it would have a section in there. I hope that makes sense. This is our chessboard pattern starting, and normally we would expect to continue, but these 2 factors here are causing the problem. What happens at this point is that when the coefficient turns to negative in here, before it changes back to positive again when it gets past the next point, but where it changes to negative, it thinks, no, our graphs don't actually think, but it behaves as though we've done the negative job here and here and here and so on. Now, if we had done this graph, you can see the graph would expect to go up here. If it had been negative. So the graph is actually going to cross through the asymptote there and go up. Now, interestingly, if in this little panel it would have been here and here, and then diagonally down here, and diagonally across here, and diagonally down here. Well, guess what? The graph's going to go through that point, and go through this point, and go through this point. So you've succeeded in creating a bit of a monster, actually. This is not obviously a function. If you do your vertical line test, you're going to have multiple places where the graph is where you're going to have values for the y values for the same x value. So your vertical line test will fail. It's a relation but not a function. Now, once we get from past this point, where x is -3, it wants to switch back the other way again. So instead of being in here and up there, and here and down here and doing the checkerboard, it suddenly wants to switch back to this side. There we go. You can try and feed that into Wolfram Alpha, and I haven't done it, but I suspect it will have difficulty graphing that. But believe it or not, that's the sort of graph you get. Now you can explore, this is easy to experiment with. You could change one of these to y plus 2x. So suddenly you've got an oblique axis, oblique asymptote. Or one of them could be y minus x cubed, or x squared, y plus 2x minus 3. So you can actually not just have horizontal asymptotes here, but you can actually have oblique or even curvilinear asymptotes. You could square some of these so they become double asymptotes, in which case it gets quite complicated because things start to want to reflect, and that becomes an interesting challenge. But I encourage you to explore this. Now, I've used a deliberately difficult example. Try and do it with just 2 of each or something like that, and one changeover point, and see whether you can get a zigzag happening. With simple ones, Wolfram Alpha might be able to graph it for you. But that's all I wanted to show you in this video. If you've enjoyed it, please like it, leave a comment, subscribe if you're not already a subscriber, and I thank you very much for watching.